Okay, so I just wanted to go over the survival guide sheet that I made for you as an introduction to how to calculate the volume of a solid with known cross sections. So to explain this to you, I want to go back to two things. First of all, the work we did a couple weeks ago on area, because volume is connected to area, and then go back even further to some of the work we did in grade 9 around area and around volume, and see if we can make connections about how that works with the shapes that we're going to be looking at in calculus. So first of all, we'll go back to, we'll start with area, and we'll go back to grade 9. So here I have a rectangle, and I'm going to call this here the length, and I'm going to call this here the height. And if I asked you in grade 9 to find the area of this rectangle, you would tell me, well, that means we know that the area is equal to the length times the height. Length times height is ln. And if you remember, when we started talking about Riemann sums back in March, and we wanted to use Riemann sums to help us estimate areas under the curves, what we did is we took shapes like this, or a curve like this, and if we wanted to find the area under the curve, then what we could do is we could visualize a bunch of rectangles under the curve. And if we take those rectangle areas, we called the height of those rectangles f at x. So the height here is determined by the height of the curve. So that's our height of the rectangle. And our width, or our length of the rectangle, we call delta x. And that's determined by how thick we decide we want our rectangle to be. So if we take our delta x times our f at x, then we can find the area of the individual rectangles all along this interval. And if we take them and we sum them up, then we would have the area under the full integral. So we have the area underneath this curve is equal to the sum of the areas of all the rectangles. Well, we know that that's the same as the area of the heights, which is f at x, times our lengths, which are delta x's. And then we took that and connected it to an integral. And so we know that if we make these x's infinitely small and take the limit as delta x approaches infinity, then that means that the integral from a to b of f at x dx would give us the area. So that delta x just became our dx, and our heights are represented by the function f at x. So the area under this curve with the calculus connection is that the area is equal to the integral from a to b of f at x dx. And that comes from the idea of finding area of a rectangle that we looked at in grade 9. So connecting that to formulas then, we know that the area, if we're looking at a curve like this with respect to the x-axis, is going to be the integral from a to b of f at x dx. And if we flip this on its side and we do it with respect to the y-axis instead of the x-axis, then we know we take the integral of c to d of f at y dy. Okay, so that's all material that we've covered before. And what we want to do now is we want to take this idea and connect it to volume. So going back to grade 9 once again, I'm going to take this rectangle, it's 2-dimensional right now, and I'm going to make it 3-dimensional by giving it some width here. So I still have my rectangle with a length and a height, but the width makes it a rectangular prism. So now, if I'm going to make a calculation with this, I'm going to calculate the volume of it. So to calculate the volume of this rectangular prism, I'm going to take my length times my width times my height. And in this case, my length is here. And then my width and my height, if I multiply those two together, I'm going to get the area of this rectangle right here. And that's like the face of the rectangle. So if I kind of spin this around and look at it, I'm going to see the rectangle that has an area of width times height. So the length times the area of the face of that rectangle will give me the volume. So now if we take the same idea we did here, we want to connect it to calculus and be able to calculate volumes of solids that have more, have shapes that aren't quite so regular as a rectangular prism. So if I have this curve here, so I need you to visualize this. So we have a curve here, it goes from A to B, what's shaded in here. And what I'm going to do is I'm going to make it three-dimensional by making squares kind of in the direction of the z-axis. So I've got my x-axis, my y-axis, and then I'm just going to put the z-axis coming out here. So I'm going to make cross sections of squares, making it three-dimensional. And then I'm going to carry those squares, so no matter where I cut it, I will always have a square right here. Okay, so again, I can take this idea here of looking at my areas of my rectangles, and now I can split this three-dimensional shape up. So now I have volumes of prisms. So you can kind of see this prism right here. It's a rectangular prism. It has a length here, and we're going to call that delta x, where length here is like our length here. We'll call that delta x. And then our width and our height, our width here and our height here. The height is going to be determined by the height of your function. So f of x will be our height. And when we do the width here, there's usually some kind of connection to your height. So in this case, we'll just say that, let's just say that we have this area of the face here. So if we have the width and we have the height that's determined by f of x, then we'll just call this area here a at x. So a at x is just the area of the rectangle or the square or whatever shape it is that will be the face of this three-dimensional figure. So if we take the same idea then, here we have the sum of our areas of our rectangles. To find our volume, we're going to take the sum of the volumes of the prisms. And to find the volumes of the prisms, we find the area of the face of the prism, which would be this piece right here. And that's determined by usually some kind of connection to the height or the function that you're working with. And you're going to times that by your delta x, which is your length right here, just like we had our delta x, this is our length right here. And I can turn this into an integral by saying that the volume then is equal to the integral from a to b, which is the sum, of the area of the faces, which is this guy right here, so whatever the area of that would be, times that length of my delta x. Okay, so we took something that was two-dimensional, our integral to find the area under the curve in 2 dimensions, and made it 3 dimensions by connecting your f of x to an actual area of a surface or of a cross-section of that solid. Okay, so just like we had formulas then for area under a curve using our integrals, we can do the same thing with volume. So volume, if we want to look at a cross-section that is perpendicular to the x-axis. So you notice that here I have, when I make my Riemann sum of my prisms, my Riemann sum cross-sections of my prisms are all vertical lines that are perpendicular to the x-axis. So in this case, I want to look from A to B. So the volume from A to B of all of my areas times my widths, so the integral from A to B, A to AX dx, would be the volume of the cross-section with perpendicular to the x-axis cross-sections. If I took this and flipped it on its side and looked at it with reference to the y-axis, the cross-sections would become horizontal. And that would change up our formula a little bit, because now we would be looking at horizontal cross-sections that are perpendicular to the y-axis. So if that's the case, if we want to look at it with reference to y instead of with reference to the x-axis, then we just switch up our variables. So I'm going to call that v is equal to the integral from c to d, because we're looking at c to d values on the y-axis, of a with respect to y, so the area with respect to y of dy, because our dx's would become dy's when you look at delta y's instead of delta x's here. So very similar idea here. You just take this one step further and make it 3-dimensional by taking our function and changing that function into the area of a face of our cross section and then timesing it by our length in order to get the 3 dimensions.